Okay, so we start the lecture now. So we have several topics today. First, we want to do the lab session for bugging random forests and boosting. So I will review the materials a little bit. Then we discuss our implementation of those methods. Then we do exercise. The exercise for today is already available on the website in Canvas, so you can see the exercise sheet. Yeah, and if we have more time, we will go into chapter 9, that is support vector machine. But probably that we don't have that much time. Do you have any questions about final projects or last lecture so far?
Not at this time.
Good. Okay, so I will share the screen and I will start the class. Okay, so a quick review for bugging the random forests and the boosting. So we have studied the regression tree. So regression tree is basically that we separate cases by splitting the predictor space. So at each time that we use one predictor to separate the predictor space. For example, in this case, that we separate this value, maybe x1 is equal to some constant a. Then more than x1 is more than a, or x1 is less than a. We separate two cases and we fit the regression model for each part. And usually we just use constant to fit each region. So this is the piecewise just constant function. So in this case, that we use the 1, 2, 3, 4, four nodes for the tree, and we have 5 pieces. The predictor space was separated into 5 pieces, and we fit the constant for each part. But you can see the regression tree is the fitted value for the regression tree is very, discontinuous. So we want to have more smooth curve, the more gradual the steps we would like to have. So that is the idea of the random forests or bugging. So bugging, basically we make a regression tree multiple times and take average. And of course, if we use just the usual regression tree, the b times, then all trees are the same. So we do random sampling first, then we fit the regression tree, and we repeat and take average. So that is bugging. And the next one is the random forests. So random forest is almost the same as bugging, but only the difference is only the difference is that for each time to make a tree, that we allow to use just a few predictors out of the total p predictors. So usually we only allow the 1/3 of the existing predictors to make a tree. Or sometimes we use about square root of p. So if p is 100, then we use only just 10 predictors to make each tree. So then we have more variety between trees. Then sometimes prediction performance is better. Or we can say that the m is a hyperparameter. So if we optimize hyperparameter, then we can adjust the model to the data set so that we can we can have a better model. So parameters have pros and cons. So if we have more hyperparameters, basically we can search for a better model for that specific data set. But on the other hand, the control is more difficult. You have to choose parameters. So maybe you can use cross-validation, but we have more steps to see what are the optimal parameters. And those are the bagging and random forests. So these are similar methods. And boosting is another technique. Actually, this is more general technique to improve model performance, prediction model performance. And here, of course, we are doing the tree-based methods. So we apply the boosting for tree-based methods. So the idea of boosting is the slowly fitting a statistical model. So we make some model and we just reflect the part of the regression result, I mean, a model result that to the our model. Then after that, we think about the residual of that model, and we fit the residual on the predictors and again. So boosting is kind of similar to bagging or random forests in the sense that we make many trees, but the boosting is more sequential. And the sequential methodology is generally good for regression analysis because you know we can do different thing in each step. So if we do two trees based on the same data set, then usually the two results are similar in any way, even we randomize. But boosting, we make a tree. Then after that, we think about the residuals. Then we fit residual on the predictors, so it makes a difference. Right? Yeah. For example, maybe another example of the usefulness of the sequential method is maybe polynomial regression. So think about the y is equal to beta naught plus beta 1x plus beta 2x square plus the beta 3x cube plus epsilon. And suppose x is in the range, for example, maybe the 0, 1. Then you can see x squared and x cubed are very similar. Even x are also similar. You can see the x-axis, y-axis, and x, y. And if we think about x squared and x cubed, these are similar functions. So almost indistinguishable. Maybe this is a kind of exaggeration, but if we think about x to the 4th power, 5th power, then it's very similar. So that's why if we fit this model, then we have a lot of, we have a severe multicollinearity on higher order terms, such as this and this. But if we fit, for example, y is equal to beta naught plus beta 1x plus epsilon, maybe epsilon 1, I would say, then we use the estimated epsilon 1 hat, and we fit this on beta 2 hat plus x squared. Sorry. Sorry, x1, we fit the model, then we get the residual. Yeah, then we fit the, I think that we need maybe once again the gamma naught plus gamma 1x plus gamma 2x3 plus epsilon 2. Then the fitted curve is orthogonal to the original predictor because the x part has already removed from epsilon 1. So then we fit another maybe cubic curve, for example, epsilon 2. hat, estimated epsilon 2 hat on the maybe the delta naught plus delta 1x plus delta 2x square plus delta cube x cube plus epsilon 3. Yeah, maybe this isn't a very good example, but then this component is orthogonal to the previous two components. So 3 yellow components are all orthogonal. So basically, if we do the regression sequentially, these components are more independent. In this boosting, they're actually not entirely independent, but at least we are doing different thing. So that is a good thing to do, because we have the more diversity among this estimated f hat b. Okay, so these are the bagging, the random forest, and the boosting. And the last time that we did the regression tree and the classification trees, so that we do the bagging and the boosting this time. And the last time, just a quick review on the performance of the 3 methods for the regression. So yeah, I updated this chapter 8L, the lab slide, and we are doing the forecasting for this car seats data. So we have the 400 observations, and we want to predict the sales of each store of car seats. And the tree-based methods, the out of sample performance, I mean the test RMSE is about 5.0, 5.1 for regression tree. So this is the training error, and this is the test error, the mean square error, sorry, not R mean square, root mean square, but the mean square is about 5.1. This is the regression result. But if we do actually linear regression with the stepwise procedure, then actually the test performance is 1.09, so it's much smaller. So 5.1 and 1.9, 1.1, about 1.1. And this time the bagging. So bagging, we use the library random forest, because the random forest and the bagging are almost the same model. So we use the same function. So actually the bagging can be done by random forest function by specifying the m try is equal to 10. M try is the number of predictors in each tree. So remember that this car seats data, we have the 10 predictors, so x1 to x10. So these are the shelf location, or the competitor's price, or the country of origin of car seats, or something like that. So x1 to x10. And so here that we allow all predictors each time to generate tree. So that is bagging. So if m try is smaller, then that is a random forest. And here is the result. So at first, this shows the overall contribution of each factors. So we have actually the 10 predictors, and this explains the when the variable is dropped, then how much the mean square error gets larger. So if we include all 10 predictors, we have some MSE, suppose that is case, so alpha. Then if we drop the competitor's price, then the MSE, the size of MSE gets 17%, 18% larger. So this is a kind of the just leave one out influence. So when we drop this variable, the MSE increases by 17.8%. So that means this has somewhat the large impact, but for example, the income, this doesn't have really a large impact because it increases only by 0.1%. So probably the significant variables are maybe these ones, right? And others are probably maybe this one, and others are probably they're not very significant. So tree-based method is not likelihood-based. So we don't have any specific test, but we have some quantitative information on how much the MSE is increased. So another one is node purity. So this is just another measure that's similar to MSE, but the increase of that amount. So you can see mostly that this is similar to the first column. And this is just a graph of that. So increase in the MSE and increase in the node purity. Yeah, and the node purity is actually here the yeah, so node purity is defined as the increase in residual sum of squares for regression and the Gini index for the classification. And I thought that this is the same for regression case, but it sounds slightly different between this and this. Yeah, so maybe the detailed algorithm is slightly different between the percentage increase in MSE and the increase in node purity. Yeah. Sorry that I'm not 100% clear why that these two don't coincide in this case. And for classification problems, we use this so-called Gini index, so it's different from the MSE. So that is certainly different. Yeah, then we make a prediction, and we fit the we just plot the predicted sales and actual sales. So if this is perfect, then all points are on a line y is equal to x. But here we have the pretty high correlation. So this prediction is good for training data set. But generally, the tree-based method has the severe overfitting. So if we do this for test data set, we can use the predict function with the new data option. Then we have the much lower correlation coefficient between the actual ones and the predicted one. Sorry, I think I switched this one. Maybe we should put predicted one on the x-axis. But anyway, so you can see the correlations are different. So for test set, correlation is much lower. And this is the difference between the predicted and the actual and squared and take mean. So the mean square error. So mean square error is about 0.478. That is extremely small for training data set. So remember that the stepwise selection of linear model, both training error and the test error are about 1.1. So MSE, so linear model. Both training error and the test error are 1.1, about 1.1. That's natural because we, possibly training error is slightly larger, but we have used the stepwise procedure. So we optimize test error. So the difference isn't really too large. And here, 0.477, but it's very small, very small. Compared to 1.1, it's less than half of that. But actually, the test error is 2.877. So it's believed that the bugging and random forests are really good methods, but for this example, it's not as good as linear model. Linear model is much better because test error is only 1.1. Why? I don't know, but it depends on the data. So sometimes the bugging random forests perform much better. Okay, so here the random forests. So random forests are the same as bugging, except for the fact that we allow only few predictors. We allow only a few predictors for each tree. And again, this is the training predicted value for the training set and actual value, actual sales for the training data set. So again, this is the training MS is 0.65. So this is slightly larger than bugging, but this doesn't really matter because this is training error and it's much smaller than linear model. So how about test error? And it does not look really good. So still correlation is not very high. And actually we got the error of 2.95. So actually we use just the typical parameter m that is about 1/3 of the 10, the number of predictors, and also this is close to the square root of 10. So it's a typical parameter, but actually it does not really improve the situation. So probably the true the hyperparameter m is closer to 10. So actually the test error is 2.95. So again, this is much worse than linear model, and that just depends on this data set. So I don't know, for this data set, linear model really works well. Yeah. So I haven't make any plots, but probably the many relationship is more linear. So if the relationship between the predictors, a predictor and the response are really linear, then it's really inefficient to use the tree-based methods. If the linear regression, if this situation, you can immediately see this kind of straight line. But if we use the bugging or random forests or just tree-based regression, we separate and take average, then we separate and we again separate this or something like that. So it's not really efficient. So tree-based methods are not really efficient. So in this data set, the linear model works better. Okay, so this is the random forest, and the next one is the boosting. Do you have any questions so far?
No, looking forward to this.
Yeah, so only thing you have to choose is the M try, so the one per hyperparameter, but you don't have many choices unless the predictor value is too large. So yeah, and the next one is the boosting. The boosting, we have two examples. So one is for Cassit's dataset, the same dataset as 8.2. And another one is Boston dataset, which is also popular, the housing price data in MASS package. And for boosting, we use the GBM package. And we use the GBM, the function. Generalized boosting some. I'm not exactly sure what it stands for, but the BGM function. And the format is similar to LM or random forest. So just the predictor tilde, the response tilde predictors. And we use the training set, the same training set as before. And we have to specify the distribution function here. So we should use this as Gaussian, so that we minimize the basically the mean square error. So yeah, and the if this is classification, you have to specify the distribution is Bernoulli. So the the classification 0, 1 is called Bernoulli in mathematics in general. And here the number of parameters, some hyperparameters. So this is the number of trees, that is B. So basically larger is better. And the another parameter lambda is a step size. The step size is, I'm not exactly sure about the option name, but you can specify the step size. Step size is small, then we need large B. So yeah. And the step size, I think the default is 0.01, maybe 0.01, and 0.1. I'm not exactly sure, but we have some default value. And this is the interaction depth. So basically the number of predictors allowed to make each tree. And the textbook suggests the interaction depth is usually 1 or 2 in many examples. But for this one, actually the 6 was optimal when I fit the model. Yeah. And yeah, and this is the result, the summary of this, the boosting. And this is similar to, I'm not exactly sure about the how this statistic is calculated, but this is similar to the percentage increase in MSE when the variable is dropped. So the shelf location is the most important variable here. And this price and competitor's price and age income, so these are useful variables in order of importance. And also the same information as a table. Yeah, so LAS is equal to 1. So this makes the names the horizontal. Actually, textbook's example, these names are vertical, so we cannot really see. Yeah, you can see the textbook. And we can make a plot. This is just a marginal plot for response and one predictor. So price and shelf location are 2 of the most important predictors. So we make a graph of price against the response and also shelf location against response. And you can see that this is not really it's not very smooth, but it's almost a smooth curve, and it looks almost continuous. And this is shelf location. So we have shelf location. I think that we only have 3 values. So actually this and this and this, but you can see that for each shelf location has the different level. Yeah, I think that I'm not also exactly sure how these graphs are calculated, because this is our fitted value and we have 10 predictors. So how about the level of the other 9 predictors? Probably they impute the mean predictor value. So we have just the price and y. So we have 9 other predictors. So probably they impute the mean value for other 9 predictors. Then we can see the relationship between price and the response. The response is sales. Yeah. Then you can do the test. We can calculate test error. So the predict by using predict function. So it sounds that we can update the number of trees again, but just I fixed it as 5,000. It sounds 5,000 is sufficient number. I changed it into 10,000. The result doesn't change, almost the same. A very small difference maybe, but the almost no difference. And we can calculate test error, and that is 1.357. So it's a kind of surprising that the linear model is still better than this, but it's almost similar. Yeah, so random forest and the boosting, sorry, the bugging and random forests have much worse performance, about 2.8 or 2.9. And the boosting 1.35, so it is much better, but still it's worse than the linear model that's chosen by step function. And this is difference between the test MSE by interaction depths. So yeah, actually the 6 is the best, and the smaller one works reasonably well, but still the 6 is the best. So even though we only have 10 predictors, and the textbook suggests that for in general the depth is equal to 1 or 2 is sufficient, but in this case the 6 is better than 1 or 2. Yeah, so it's still worse than the linear regression. And example 2. So this is the for the Boston dataset. So Boston datasets includes the 506 pounds of the Boston suburb, and the response is the median house value in thousands of dollars. So maybe almost all of us think that this is an error, because median house value is $24,000 in Boston. Yeah, but this is data from 60s, so this is very cheap. The houses are very cheap. Okay, and we set the training set and the test set, and we want to predict by this boosting methods, so GBM function. And this is still the regression example. So distribution, we have to specify the Gaussian. So our criterion is basically the mean square error. And you can see this LSTAT and RM. So these are really important predictors, and others have some value to explain the Y, the median house value. And this is the same information in table. And this is again the graph. The RM is the average number of rooms per dwelling, and versus Y. So it sounds different from these days. So these days, the smaller number of bedrooms is sometimes more expensive, because we have more expensive features, such as more bathrooms or larger kitchen. But still, if we fix other parameters, maybe, if we don't have other information, then this is maybe useful as well. And LSTAT is lower status of the population in percent. Of course, it has the negative relationship with housing price. So this is a kind of obvious relationship, but these two. And we can calculate fitted value by predict function again, and we can calculate the test root mean square error. So this time I take the square root, because I saw the analysis of this data many times, and I know what's the good RMSE. And actually the RMSE for the test set is 2.73. This is pretty small. So usually it's hard to get less than 3. So 3, 3.1, 3.2. So these are good numbers. If you just fit linear model, usually you can just achieve the 4.5 or something like that. So this method works very well for this data set. I don't know exact reason, but it's the case for this example. Yeah. So for some data set, these methods do not work well, but some data set it fits very well. And these days we have more advanced method based on the regression trees, such as the XGBoost. Yeah, XGBoost. We don't cover this today, but so yeah, so these are the results. Okay, so do you have any questions on boosting? Okay, so now we do exercise. Oh, this is solution. Okay. So we use Caravan dataset in ISRR package, and I don't show this dataset, but this is very large dataset with 5,800 observations and for 86 variables. So we just use this as just a big data. So I don't interpret data, so it's too hard to interpret all predictors. But this is basically the socio-demographic data and the product ownership data for some customer records. And so basically we want to, so this is marketing data. So this is marketing data. So we want to identify which customers they buy the product. And if we use this, it is useful, for example, to advertise the product to consumers by mail. So we identify the good potential customers out of 5,800, maybe out of the test data set, and we send the advertisement to those customers. So some people are not likely to buy the product based on the socio-demographic data and some other data set, some other variables. Yeah, and yes, the socio-demographic data is derived from the zip codes. So the zip code is just one column, but it is connected to income level, crime rate, and maybe some racial decomposition, and the educational level, many other variables. So these variables are derived from the zip code. And all customers living in the area with the same zip code have the same socio-graphic attributes. So we have a kind of factor variable, but with many values. And the last variable is whether or not the customer purchased the caravan insurance policy. So yeah, so the response variable. So this is classification problem. So yeah, so question is at first create the 1,000 observations as a training set, and the other observations as test set. Here, I don't ask you to randomize. So it sounds this data set is originally randomized. And then they fit the boosting model and with this specification, and then they get the table. So usually we put just 0.5 as a threshold whether or not the customer buy the product, but actually not many customers bought the product. I think you can investigate it, but only a few % of customers bought it. So it's very hard to find the customers who are likely to buy the product with more than 50% probability. So we set 20% as threshold, and we divide the people into people who are likely to buy product with more than 20% probability and less than 20% probability. Then we do the same thing by random forest and also the logistic regression. So that is the question. Okay, so now that we separate the group into how many people here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 6 people. So maybe I split the room into 2 breakout rooms, so you can discuss the problem about maybe 20 minutes, 25 minutes maybe. And Hunter. want to call it. Okay, we start. Okay, so 20 minutes. Oh.
You're still muted, Professor, if you're saying anything right now.
Thank you. So we have to load the data, ISLR for data, and a GBM and a tree-based. Maybe we don't use this, but also a random forest package later. And the training set, okay, so at first, the response variable, we want to make yes into 1 and no into 0. But originally, it's coded into no is 1 and yes is 2. So that is alphabetical order. So this is 1 and this is 2. So I just make it numeric and subtract by 1. Then yes, no becomes 1, 0. And training set, first 1000, next the others. So one reason I asked this is just to get the same result. If we randomize, the result may be randomized again. And boosting, at first, B is boosting, right? This is B is boosting, yes. So boosting, we have to specify B and the kind of step size, the shrinkage 0.01, and the interaction depth, this is 2. Okay, I think this is, sorry, I specified 1, I don't know. 1. Yeah, 1, sorry. The 1 and the 2 have the only slight difference. Maybe that should be 1, right? And we can do that. And I changed something and we get this. So the useful predictors are maybe these predictors, okay? So you can see maybe half of the parameters are useful and the other half probably not at all. I don't know what this predictor means, the PPAR, SAUT, or MKOOPKLA. I'm not exactly sure about this. But we have a list of predictors. Then we make a prediction. And a prediction, oh, sorry, maybe before that, we have to mention that this is binary response. So the distribution should be the Bernoulli. So Bernoulli. And I used the number of trees equal to 1000. Probably that is sufficient size for this problem. And predicted the GBM. Yeah, and I think the lambda times B is somewhat important quantity. So here 0.01 and the B is 1000. So if lambda is 0.001, maybe B should be much larger. And this is predicted value. So type is equal to response is needed. So when you use predict function, sometimes the transformed numbers appear. For example, logistic regression, I think it returns. I think the logistic scale, the inverse logistic scale. So we have to specify type is equal to response to get probabilities. Then the threshold is 0.2, so we specify this. Then we can make a table. So I think the room 2 uses the confusion matrix function. Yeah, there are many functions, but we can simply use table here. And here predicted value is here. So for training set, it's good. 35 out of 66 observations are actually the people who purchased the product. So this is about maybe 55%. So on average, not on average. So at least these people, each of these people have more than 20% probability to buy the product. So the number is larger than 20%. So that looks good. It sounds like if we send these 66 people direct mail, then 35 out of those buy the product, would buy the product. But for the test set, we can do the same thing. Then we get this table. So only 35 out of 35 plus 171 people bought the product. So this is about only 17%. So this is less than 20%. This is contradictory to our model. But basically, this model does not work that good. But of course, it makes some sense. So the other group, the predicted false group. So this ratio is 254 divided by 254 plus 4,362. So that is only about maybe 3%, maybe more than that, maybe 5%. So much lower than this 70%. So it makes some sense to make a prediction, but this 20% threshold isn't really that reliable. And random forests, you can just follow the same procedure as the example. So you can use library random forests, and you can do the same thing. And actually, I try the number of trees is equal to 9. This is about maybe square root of the number of predictors, because the number of predictors is 85 or something. And the performance is not really good as well here. So 0.14. So 14% of people predicted purchasing the product, bought the product. And this is logistic regression. And when I fit the logistic regression, I have the severe overfitting, almost the perfect model appears first. In such a case, the AIC does not work well. So I decided to give a forward selection. For forward selection, we have the starting model and the range of the model. The GLM0 is the null model. GLMF is the largest model. So basically, we have to specify the scope, I think. Maybe some of these can be omitted, but basically the starting model and the scope, the minimum and maximum model, and the direction, then trace 0. Then these are the predictors chosen. Only maybe 10 or 15 predictors. And actually, if we calculate the fitted value, you can see that the very few observations are categorized as more than 20% probability. And we make a prediction table, and this is predicted. So the 39 out of 39 plus 175 bought the product. So this is about 18%. So it's comparable. So the old model are not good enough to guarantee 20% chance to purchase, but it works somewhat well. So this percentage is much higher than overall average, or this percentage. So this one is just 250 over about 45,000. So this is about only 5%. So still, it's much better. So that's the point. And if we calculate accuracy of this model, random forest or boosting, so of course this is high, but this is basically because most people don't buy the product. If we predict that no one buy the product, then it's 90% correct. So it's not really a good result, but just the baseline is high for accuracy. Okay, so almost that's it. And just I want to add one thing that I didn't explain well last time. So so percentage increase in MSE and increase in node purity. Percent increase in MSE is based on out-of-back sample. So it's a kind of similar to test error. And the node purity is calculated based on the overall all trees. So it's a kind of closer to training error. Maybe both are somewhat in between. But so that's why these two are different. Okay, so that's it for today. And do you have any questions? Okay, so if not, then see you on Wednesday.
See you.